Imagine draining every drop of energy from the universe. Every star extinguished, every atom frozen, every particle motionless. A universe at absolute zero. Nothing left. Or so it seems. Yet physics tells a different story. Even stripped bare, something remains, an invisible energy woven into reality itself. This is zero-point energy, and it overturns our understanding of emptiness, energy, and the universe. At first, it sounds impossible. How can empty space contain energy? The answer lies in quantum mechanics, where nothing is ever fully at rest. Even at absolute zero, particles vibrate with a baseline energy. This is zero-point energy, the irreducible minimum of quantum systems. It is a hum that persists, an undercurrent to the universe's symphony, even when all other motion has ceased. To grasp it, we must enter the quantum vacuum. Far from empty, it is a restless sea of particles flickering in and out of existence. These fluctuations arise from quantum field theory and the Heisenberg uncertainty principle, which forbids exact knowledge of both position and momentum. Thus, even at lowest energy, the universe cannot be still. That residual motion is zero-point energy, an unavoidable feature of reality. Evidence comes not from speculation but experiment. In the 20th century, Hendrik Casimir predicted a subtle force acting between two plates in a vacuum. Known as the Casimir effect, it occurs because the quantum vacuum behaves differently between plates than in open space, producing a push that draws them together. Repeated experiments confirm this, showing the vacuum is alive with energy, an unseen ocean beneath stillness. The implications are profound. Calculating total vacuum energy yields staggering values, far beyond observed reality. This mismatch forms the cosmological constant problem. Predictions exceed observations by an unimaginable margin. The universe clearly isn't torn apart, so something fundamental is missing in our understanding of space, energy, and gravity. Zero-point energy sits at the heart of this mystery. Yet it is not merely theoretical. It has measurable effects on atomic interactions, tunneling, and the stability of matter. What we call empty space is a dynamic medium shaping everything within it. For centuries, people have dreamed of tapping this energy. If accessible, it could be a limitless power source, transforming technology and civilization. But physics imposes strict limits. Zero-point energy is a baseline of reality itself, not a reservoir to be drained. Extracting it without violating conservation laws remains impossible. Consider the analogy of an ocean. Even on calm days, the surface ripples. Zero-point energy is that ripple, present even in void. For physicists, these ripples are vacuum fluctuations required by commutation relations. For others, it is simply the truth that nothingness is never empty. Its story is entwined with cosmology. Dark energy, the mysterious driver of cosmic acceleration, may connect to vacuum energy. Einstein's cosmological constant, once abandoned, later reappeared in light of modern observations. Though the connection is unclear, it underscores the significance of zero-point energy, bridging quantum mechanics and cosmic fate. Experiments continue to probe this hidden energy. From the Lamb shift in spectra to spontaneous emission and vacuum polarization, zero-point fingerprints are everywhere. Even the stability of matter depends on them. Without zero-point energy, atoms and molecules could not exist. Beyond the lab, it challenges philosophy. Space is not passive void but an active participant shaping forces, interactions, and spacetime itself. Zero-point energy proves the vacuum is alive, forcing us to rethink emptiness. Proposals to extract usable power usually violate thermodynamics. Any breakthrough would require deeper knowledge of quantum fields and spacetime itself. Still, curiosity persists. The concept inspires thought experiments, speculation, and fiction. It invites visions of civilizations mastering the vacuum, while motivating physicists to test the edges of possibility. Early pioneers like Planck and Heisenberg recognized the inevitability of residual energy. Later, quantum field theory formalized it. Experiments across the 20th and 21st centuries confirmed predictions. Each discovery showed the vacuum to be far richer than once imagined. Zero-point energy also raises questions about cosmic destiny. If the vacuum holds vast energy, what role does it play in expansion, galaxy formation, or entropy's limits? These remain unanswered, but they highlight zero-point energy's significance as a cornerstone of physics and a window into reality's deep structure. Its influence extends to the microscopic. Quantum fluctuations drive chemical reactions, affect superconductors, and shape subatomic dynamics. They limit measurement precision, dictate atomic stability, and underlie matter's structure. Understanding zero-point energy is essential for a complete quantum picture, linking theory with observation. Naturally, one wonders if humanity could ever manipulate it. While current physics suggests enormous barriers, the pursuit itself pushes science forward. Investigating the vacuum reveals insights into electrodynamics, particle physics, cosmology, and perhaps the unification of forces. Each experiment illuminates a corner of reality that would otherwise remain hidden. Zero-point energy embodies the edge of science, where math, measurement, and imagination converge. It urges us to test assumptions and recognize richness in emptiness. It inspires questions about the limits of knowledge, the reach of technology, and the shape of reality itself. Looking ahead, it challenges engineers, physicists, and philosophers alike. Can we expand our notion of energy? Can we harness principles hidden in the vacuum? What consequences might follow? The universe offers this energy freely, but only on its terms. Humanity must discover what those terms mean. Ultimately, zero-point energy reminds us the universe is more mysterious than it appears. Space is never empty, silence is never still. Every fluctuation contributes to an unseen backdrop shaping atoms and galaxies alike. Even as we probe with greater precision, questions remain. How much energy truly lies in empty space? How does it influence dark energy and expansion? Could new principles allow interaction in ways we cannot yet imagine? These questions drive modern physics, revealing a universe stranger than experience suggests. Zero-point energy is not just abstraction but a lens altering how we see existence. It shows emptiness is never absolute, reality never simple, and knowledge never complete. It leaves us wondering, if the cosmos hums with hidden energy, what potentials lie within it? Could it hold keys to unimaginable technologies, or is it the subtle framework that keeps balance? The answers remain beyond reach, but the search continues, uncovering secrets of the vacuum and limits of human understanding. Even in the quietest corners of the cosmos, the universe is never silent. It hums with activity, vibrates with potential, and challenges perception. Zero-point energy redefines nothingness, reshapes physics, and remains one of reality's most profound mysteries. We may not know all its secrets, but we know this much: nothing is ever truly nothing, and the universe is richer, stranger, and more alive than we ever dared to dream.